working fluid, we will begin our study of the Brayton cycle with the following assumptions. The working fluid is air, which continuously circulates in a closed loop and behaves as an ideal gas. All the processes that make up the cycle are internally reversible. The combustion process is replaced by a heat addition process from an external source. The exhaust process is replaced by a heat rejection process that restores the air to its initial state. These four approximations are known as the air standard assumptions, and they can be applied to all gas power cycles. We will use this closed cycle to model the gas turbine. The compressor's function is to increase the pressure of the air. Since work is being done on the air, the compressor requires work input. The work input for this compressor is supplied by backwork from the turbine. The TS diagram for the isentropic compression process is shown. When changes in kinetic and potential energies are negligible, as we discussed earlier, the conservation of energy equation reduces to Q minus W equals delta H. Since heat is not transferred between the compressor and its surroundings, the work input becomes equal to the change in enthalpy. Recall that enthalpy is a function of temperature and pressure. The enthalpy-entropy, or HS diagram for the compression process, looks similar to the TS diagram. Here, H1 and H2S are the enthalpy values at the inlet and exit states of this isentropic process. H2A is the enthalpy at the exit state of the actual compression process. A compressor's performance is often measured in terms of its isentropic, or adiabatic efficiency. The adiabatic efficiency of a compressor is defined as the ratio of the work input required to raise the pressure of a gas to a specific value in an isentropic manner to the actual work input. The adiabatic efficiency is greatly affected by the design of the compressor. Well-designed compressors have adiabatic efficiencies that range from 75 to 90%. Another way a compressor's performance is measured is by its polytropic efficiency. The pressure and volume at the state points of a polytropic process are related by an arbitrary exponent, n. The compressor designer is concerned with the polytropic efficiency across each stage of the compressor. Designers produce polytropic efficiency curves that can be used in performance monitoring. These performance measurements also apply to compressors that are being driven by other prime movers as well. A compressor map is a way to determine performance by including other parameters. The typical map uses corrected mass flow rate, corrected rotor speed, polytropic efficiency, and total pressure ratio for the performance parameters. The corrected parameters are determined by a ratio of the current temperature and atmospheric pressure to the standard temperature and pressure at sea level. The combustion process is how energy gets added to the working fluid for the Brayton cycle. Energy is added to the air in the form of heat. In the actual combustion process, there is a pressure drop between the combustor inlet and the turbine. This pressure drop is due to friction in the working fluid. The energy added can be measured by the change in enthalpy between these two state points. Since no work is being done on or by the heat exchanger, the first law of thermodynamics reduces to Q equals H3 minus H2. Assuming the air behaves as an ideal gas, we can determine the heat input by the specific heat at constant pressure, C sub P multiplied by the change in temperature. The turbine's function is to convert the energy stored in the working fluid into useful work. Once again, we will consider the HS diagram to determine the work output from the turbine. Here, as with the compressor, the work done by the turbine is equal to the change in enthalpy between the two state points. H3 and H4S are the enthalpy values of the air at the inlet and exit states of the turbine. In the actual expansion process, H4A is the enthalpy value at the turbine's exit where an increase in entropy has occurred. The adiabatic efficiency of a turbine is defined by the ratio of the actual work output of the turbine to the work output that would be achieved if the process between the inlet state and the exit pressure were isentropic. Well-designed large turbines have adiabatic efficiencies above 90%. Notice that in the case of the turbine, the isentropic work is in the denominator. When we discussed the adiabatic efficiency of the compressor, the isentropic work was in the numerator. Why is this? Remember that we must supply work to the compressor for it to perform work on the air. Here, work is produced by the rapid expansion of air in the turbine. When work is done on a system, as is the case with the compressor doing work on the air, the isentropic work input will always be less than the actual work required. When work is done by a system, as is the case with the turbine, the isentropic work is greater than the actual work output. In our model, a fraction of the work output energy from the turbine is being used to drive the compressor. Typically, the compressor consumes about 1/2 of the total power produced by the turbine. The heat rejection process returns the working fluid to its original state when it entered the compressor. Remember that this heat rejection process replaces the exhaust process where hot gases are discharged to the atmosphere. In a combined cycle power plant, the hot exhaust gases from the gas turbine are used to help produce steam for the Rankine cycle. The heat that is rejected is measured by the change in enthalpy, or by the change in temperature multiplied by C sub P between the two state points. Ideally, we want to extract all the energy we can out of the working fluid in the turbine. That ideal process would bring the cycle to point 4 shown here. In the actual expansion process, we can't extract all the energy from the working fluid, so it is discharged from the turbine at a higher temperature. The pressure at point 4A is higher as well to account for the pressure drop during heat rejection. As we will see in the next section, the amount of heat rejected is less than the heat added to the cycle in the combustion process. We can determine the thermal efficiency of the entire Brayton cycle now that we know how to determine all the energy inputs and net energy output. Earlier we gave a general relationship for efficiency. This was the desired output divided by the required input. For the Brayton cycle, the thermal efficiency is the net work output divided by the total heat input. This calculation determines the fraction of the heat input that is being converted to net work output. We have seen that the net work output is equal to the total work output of the gas turbine minus the total work input required to drive the compressor. The net work output is also equal to the net heat transfer to the system, Q in minus Q out. The area enclosed in the TS diagram is often used to represent the network output. Notice how the TS diagram changes when we look at the actual gas turbine cycle. Here we can see how the state points are affected by the irreversibilities, heat loss, and pressure drops within the components of the cycle. When compared with the ideal cycle, we see that the heat added to the cycle is reduced, and the heat rejected has increased. This will increase the ratio of Q out to Q in, and therefore reduce the thermal efficiency of the cycle. Another parameter that is commonly used to measure efficiency is heat rate. Heat rate more readily reflects the fuel economies of the gas turbine process. Heat rate is the amount of heat added to produce a unit amount of work. The heat rate is inversely proportional to thermal efficiency, so the lower its value, the better. Heat rate is related to thermal efficiency by these equations. Each gas turbine has a predetermined output rating and heat rate that has been established by the turbine designer. This rating is valid for a standard temperature, atmospheric pressure, and relative humidity. A set of correction curves should be provided to predict what the gas turbine output and heat rate should be for other operating conditions. Let's start with the correction factor for pressure. This correction factor is determined by the ratio of the atmospheric pressure at the turbine site to the atmospheric pressure at sea level. Atmospheric pressure has no effect on thermal efficiency or heat rate. On this chart we see the effect of compressor inlet temperature on output, heat rate, and the other variables shown. The design standard temperature for this turbine was given as 59 degrees Fahrenheit. You can see that as temperature drops lower than 59 degrees, design output can increase greater than 100%, while heat rate decreases. As the temperature rises above 59 degrees, the design output decreases lower than 100% and the heat rate increases. The specific humidity correction factor can be determined from a chart similar to this one. Here the standard was 60% relative humidity at 59 degrees. This corresponds to a specific humidity of 0.0064 pounds of water vapor per pound of dry air. In this example, higher humidity results in lower power output and a greater heat rate because the air is less dense. Water or steam is sometimes injected at the compressor inlet or into the combustion system to increase power and decrease emissions. The effect of water injection on output and heat rate can be seen here. Water injection increases the mass flow through the gas turbine, so power output increases. This increase in mass flow requires more fuel for the combustion process. Therefore, the heat rate increases as well. Keep in mind that these correction curves are for a particular make and model of gas turbine. To help illustrate how the correction curves are used, we will go through an example performance calculation. The machine that these curves apply to is rated at 81.2 megawatts, burning distillate fuel at 59 degrees Fahrenheit, 14.7 psi of atmospheric pressure, and 60% relative humidity. Its design heat rate is 10,560 BTUs per kilowatt hour. From your performance monitoring equipment, you see that the actual gas turbine output is 74.34 megawatts, and the heat rate is 11,310 BTUs per kilowatt hour. Remember that the heat rate is a measure of the heat consumption to the power output. The heat rate is calculated from the fuel flow, the fuel's heating value, and the output power. The temperature and atmospheric pressure at the site are 83 degrees Fahrenheit and 14.58 psi respectively. The relative humidity is 70% at 83 degrees. This corresponds to 0.017 pounds of water vapor per pound of dry air. Water is being injected at the rate of 9.7 pounds per second. Now we want to predict what our output and heat rate should be. We determine the atmospheric pressure correction factor for output to be 0.99. The correction factors for temperature we read from the curve are 0.92 for the output and 1.02 for the heat rate. For the specific humidity, we determine the output correction factor to be 0.9985. The heat rate correction factor is 1.004. And we find the water injection correction factor for output and heat rate to be 1.049 and 1.029, respectively. The predicted output is equal to the design output multiplied by all the correction factors. The predicted output for our example is 77.46 megawatts. The predicted heat rate is determined in the same manner. When we multiply the design heat rate by all the correction factors, we calculate the predicted heat rate to be 11,128 BTUs per kilowatt hour. Why is our actual power output less than the predicted output? The results from this example indicate that further investigation and possible action, such as a compressor water wash, may be desirable. Comparing the predicted performance to the actual measured performance can help in future maintenance decisions. For this reason, online performance monitoring is valuable. Select the thermodynamics section or the Rankine cycle.